Now, so far so good. So I've got the temporal difference learning, the probabilities are not there and they are getting imitated absolutely naturally. What I'll do is I'll make in a slight change of convention called as Q learning, and the very slight change in convention will be, instead of calling a utility of S, I will call a utility of the state S given at the state S I apply the action A. Now the problem is I cannot use utility U again, so it's called as a Q value. So the Q value is the utility of state S and action A applied on state S. So the utility was defined as from S. If I follow the optimal policy and I keep going to the goal, keep going to the terminal, and every time the reward, summation reward will be different, how much of average reward do I get? That was my definition of utility. Q value is the same thing. From Q, from S, apply a mandatory action A. From S, apply a mandatory action A. After that, follow optimal policy, keep going to the terminal. And if I keep doing that infinite times, going optimally, finally, how much is my average reward average for all the infinite runs? That is my Q value. So a small change in convention. And the two are of course related to each other, because what is utility of S? It is nothing but maximum over all A Q S of A. So from S I can apply up, down, right, left. I try all of them, and once I try all of them, whichever gives me the best output is the one that I select. So it hasn't changed anything at all, and because it hasn't changed anything at all, so therefore I could of course say that from the state S I apply the action A, I get R S A S dash reaching S dash. From S dash to my terminal, I get utility of S dash, which of course is equal to maximum over A dash Q S dash comma A dash. Why not A? A was already used. So my new estimate is equal to my old estimate plus learning rate times the error. My error is observed RSAS dash plus gamma times utility of S dash, which is maximum A dash Q S dash comma A dash, minus my old value. Simple enough. So nothing really changes. It's called as Q learning now, where we are learning the joint utility of a state S action A rather than the individual state action utilities. Doesn't make much of a difference. What it does really do is that now I can look at the QSA joint values and decide my actions. It's still model free. It is still model free. It's still model free because I did not use the model anywhere in my learning. So it's still model free. God uses it. That's different. I did not use it. So it's still model free. The only thing is that it gives me some way that I can maybe estimate in the actions by some technique, by some way around. So if it was a passive reinforcement learning, my algorithm is simple. All that my algorithm says is, let all your volunteers play this dirty game, getting a point robot from source to goal with obstacles, stochastic measures, God defines it, and load all SAS dash or SAS dash into a database, and live when they are doing it, offline after they have finished, just apply this equation on every step that they take, and you make it repetitive. The moment somebody reaches the terminal and it's like, I won, you reset it at the source, let the guy play it hundreds and thousands of times. Every time a key is made, you just use this equation. Absolutely very simple. Now, the problem that I need to solve around over here is, however, that of course it's not passive reinforcement learning, it is active reinforcement learning. And therefore, let us break the active reinforcement learning problem into two parts. The first is action selection. So I say, how do I select my action? And the second one is, of course, learning from observation. So absolutely simple. The only thing that I add is a kind of action selection. So how does my algorithm go? I first reset the game and my agent is at its source, and once the agent is at its source, so I reset the game, the agent is at its source. When the agent is at its source, what do I do is that I apply the first part, which is action selection, and once the action selection is done, I implement the action. This is done by the agent and this is done by God, or of course what we call as the environment. So in a video game, you just press that key. Video game makers have whatever logic behind it to implement that action. That's a part of the environment. In real robots or their simulated avatars, you just give the motion command, hey robot, do this. Environment decides where does the robot go. So in the question thing that we were discussing, you just select the answer, then you leave it for the agent which state does the process go. So that's done by the environment. However, what you do is that the environment tells you where are you. So you are at some state, you reach the state S dash, and this is given by the environment to you. For each one of them, we have other techniques to get what is the state. Like in video games, you can actually look at the computer screen. It'll tell you what's the new state. In robots, there is an internal mechanism that always tells what's the state of the robot. Those are the algorithms that I skipped due to lack of time. So you always know what is the next state. You also know what is the reward. So all that you do is you learn using our own wonderful equation, which is this. So for this, you need the previous state known from here, you need the new state known from here, you need the reward known from here, and you therefore just learn it up. And of course, if the terminal state it's reached, then you reset the game and you start again. Otherwise, you select a new action. So in reality, you wouldn't even come to know. So the action selection mechanism looks at the new state and immediately takes the action. And the learning mechanism, it looks at a new observation and it just learns it up. So this is to be done by the environment. This is to be done by the environment. This is just to be done by interaction between agent and environment, where you just say reset. That's actually interesting because in simulators you have a physical reset. You can do it. Physical robots don't have that. So there are only two resets possible. One, take the robot and put it back at the source, or of course, terminal means that you give it a new goal and let the robot take that as a goal. So that cycle goes on. So we've already discussed this one. How do I learn? And this is what I need to discuss now. How do you select an action? So that's like the policy problem. Looking at something, I need to decide what actions do I take. Looking at something, I need to decide what actions do I need to take, and that's all. I just need to decide what is the action which is appealing as of now, and therefore that needs to be taken up. So let's go on to the action selection problem. My inputs for this problem are the Q values for current state S, and my output is action A to be implemented. Now let's look at it a bit graphically. So in that problem, this is any one of the states S. So it's a larger map divided into grids. This is just one grid out of that. And there are 4 actions: up, down, right, left. I did not tell you where is the goal, which may be somewhere here. I did not tell you what is the risk. There may be obstacles around over here. All I tell you is that the utility of this state, action up, is 80. The utility of this state, the action right, is 75. The utility of this state, the action down, is 20. And the utility of this state, the action left, is minus 10. So in all, these are what are the Q values, or Q S comma up is equal to 80, Q S comma down is equal to 20, Q S comma left is equal to minus 10, and Q S comma right is 75. Now do I really ask you that which is the best action possible? Of course it's this one. And of course, what you do is, the best action possible is the argmax over a dash qs comma a dash. So here the answer is up. Talking about it in English language, I had the Q values, and all that my system said, from this state, if I take the action up to the goal, I'll get 80 on an average. If I take down, I'll get 20 on an average. If I take right, I'll get 75 on an average. And if I take left, I'll get minus 10 on an average. And simple mathematics, it turns out that up is better. Now let's put it up in a larger perspective. So I initially have random Q values, and because I initially have a random set of Q values, a random of them is best. And because random of them is best, I believe that it's the best and I take it up. I go to another state S dash where another random S dash is the best. Hopefully I reach the goal, and yes, so I've taken a path and I learned based on the same observations. The observations change the Q values a little bit. So if it was actually bad, like leading to a collision, its value will suddenly decrease, and if it was good, leading to the goal, its value might increase. So there are some changes that I observe, and based on that, next time my agent goes, it knows those better experiences and those good experiences that it observes. So it turns out that it's not actually that bad. Or to say, small example, this was an obstacle. Initially this turned out to be a plus 80, this was minus 20, all random, plus 30, minus 100, and this was the goal or the terminal. So I took the action here, and therefore what did I do? Q32 is old value Q32 plus learning rate times error. What is error? My new observation is reward minus 1000, I got hurt, plus gamma times Q32, I landed up at the same place, of course, minus Q times 32, and this was, let's say, an old value of whatever, max over A dash. And right, left, and a left. Okay, so maximum over A dash. So I mean, this is definitely, the maximum is plus 80. So this becomes gamma times 80, and the old value was again a 80. So this becomes 80, and this becomes 80, and gamma is 0.9. So you see that this does turn out to decrease it up a bit, which is good enough. It's absolutely good. So I mean, this value will keep on decreasing, and it'll learn that, I mean, taking a left, even though it was random, was a bad idea. There is unfortunately another problem, and let me take in another example. So that's again the goal, and the value for up turns out to be plus 100, this turns out to be minus 20, plus 30. So it says that this is up, and similarly it knows that this one turns out to be plus 80, and all the way you go here. Now you get a goal which is plus 10,000. So this down gets learned, this down gets learned somehow. And what really happens is that from here you go here, and you tend to believe that it's actually very good. So by going here you get the 10,000 rewards, but it's actually bad. I should have taken this. It's clearly very bad. And that's a problem with this approach, that if your random points out to something wrong and your observations tend to agree later, if your random is initially wrong but you believe that is correct, and your observations keep on increasing, the confidence keeps on giving you more reward, your reward is increasing, you keep doing more and more and more, you get this plus 100 keeps on increasing, and because this plus 100 keeps on increasing, you're very good. And because you're doing very good, you end up believing that this is a wonderful action. Well, it's not. And therefore, this has a special term, and it's called as exploitation. I'll give you multiple examples of exploitation. So, at least at Prayagraj, the restaurants have started to operate on home delivery, though people are still not ordering. I have a favorite restaurant and I know it's good, so I keep on ordering over there. So every time I just get my food ordering app, I order it from this famous restaurant. I get great food, and every time the food delivery app sends the order to my doorstep, I get the order, I eat, I'm like, what a good experience. I go to my app and I say 5 star. So I'm increasing my confidence about it that the best Indian cuisine is at my food delivery app and my favorite restaurant. However, what happens is that at the boys' hostel, a wonderful mess vendor comes and his food is really awesome. And he delivers it at my place at a cheaper cost, so it's a better food at a cheaper cost, which is wonderful. Great food being served at Triple IT Allahabad hostel mess. However, I have exploited my favorite Indian cuisine restaurant, so I'm like, why do I try something new? Why do I eat this boys' hostel mess? It doesn't look very appealing to me, and I miss out on a great cuisine. My bad. I'll never be able to find out there was something better. And that's the same example I gave you here. So there's a restaurant that I always try. It leads me to a very good food experience. There's a restaurant that I try. It leads me to a very good food experience. I always try that. What I don't try is the hostel mess. I first asked a random guy when the mess wasn't even operative that how is the mess? The person said -20. This had 5 stars. -20. I said it's bad and I'm hesitant to try it now when it's serving great food. So I've exploited. I have absolutely exploited, and that's my bad to exploit it up. What I should have done is that I should have tried the boys' hostel mess enough number of times to know it's good or bad. What I did was just exploitation. If something is good previously, initially it was random, I say it's the best throughout life, my bad.